So our group had question number 4, which was 2-29 and 30. The question reads, the rectangular plate is deformed into the shape shown by the dashed lines. Part 1 is, determine the average normal strain along the diagonal AC and the average shear strain at the corner A relative to the XY axis. And then part 2 of this question is, determine the average normal strain along the diagonal BD and the average shear strain at corner B relative to the XY axis. In order to do this problem, we need to be able to find out the length of the diagonal, both with and without under the pressure or force. So first we find the length of the diagonal AC without the force. So what we do is we get the length of AD and the length of AB, and we use the Pythagorean theorem to find the length of AC. We do this by squaring the values 300 and 400, which is the lengths of AD and AB, and we square root them to get the value of 500 millimeters. Now, we need to find the diagonal of AC prime. We do this by adding 6 to both of them because of how it's represented in the diagram. So then we add 6 to both values of 300 and 400 to get 306 and 406. We square both values and we get the square root to find the final value of 508.4 millimeters. Now, finally, to end this, we need to use the values that we just calculated for the shear stress. So what we do is we get the values of 508.4 millimeters and the values of 500 millimeters, and we use the equation of the shear stress would be equal to the prime value that we just calculated minus the initial diagonal that we calculated divided by the initial diagonal that we have. So we do 508.4 millimeters minus 500 millimeters over 500 millimeters to get the final value of 0.0168 millimeters per millimeter.
Okay, now for shear strain at A, we use the equation for shear strain, which is pi over 2 minus theta. But we know that theta is pi over 2 minus alpha minus beta based on this figure. And if we equate those two equations, we know that the pi over 2's cancel. And we're left with alpha plus beta. Okay, now that we have alpha plus beta, we have to find alpha first. And to get alpha, if we look at the diagram, we can use tangent of alpha, which is 2 over 400 plus 3. And to get alpha, we just get the inverse of tan, which is alpha is equal to tan inverse 2 over 400 or 403, and is equal to 0.004963 radians. We know that the angle is less than pi over 2, meaning a positive shear strain.
So for number 2, it is asking the normal strain for DB and the shear strain for corner B prime, seen from the diagram. Starting with normal strain of DB, since we already found the length BD, which is 500 millimeters from previous calculations, we just need the length of B prime D prime to find the normal strain for BD. Pythagorean theorem, we can find length D prime and B prime with the orange triangle that we made in the diagram. Starting with the side A prime D prime, we can see that length from A to A prime is 2 millimeters. The original length of the box A to D is 300 millimeters, and D to D prime is 2 millimeters. To find A prime and D prime length, we have to subtract 2 millimeters and add 2 millimeters because A to A prime is 2 millimeters and D to D prime is 2 millimeters. Doing A prime and B prime length, you see that the original length from A to B is 400 millimeters and A to A prime is 2 millimeters. From B to B prime is 3 millimeters. So we have to do 400 plus 3 minus 2, which is equal to 401 millimeters. Using all these length, we can now use Pythagorean theorem to find the length of B prime D prime. So if we look at the calculation, 300 plus 2 minus 2 squared plus 400 plus 3 minus 2 squared, square root all of that, and we get 500.8 millimeters. Now we have everything we need to find the normal strain for BD. So we need the length of B prime D prime minus the length of PD divided by the length BD. That's 500.8 minus 500 divided by 500. And we get the normal strain of BD, 1.6 times 10 to the negative 3 millimeter over millimeter. Now we have to do shear strain for corner B. So we use the equation for shear strain, which is pi over 2 minus theta. And we have theta prime as pi over 2 plus alpha plus beta. And to find alpha, by looking at the diagram, we have inverse tan 2 over 400 plus 3 minus 2, which is approximately 0.004963 radians. And looking at the diagram, we see that to find beta, you have to do inverse tan 6 minus 3 divided by 300 plus 6 minus 2, which is approximately 0.009868 radians. Now we can solve for theta prime B, which is pi over 2 plus alpha plus B, which gives us 1.58563 radians. Finally, we can find the shear strain at corner B, which is pi over 2 minus 1.58563 radians, which equals to negative 0.01483 radians. And negative shear strain means that the angle is greater than pi over 2.